Okay, we're doing our AP Physics problem, and this one is about determining the greatest value of m for which these blocks can remain at rest.
Okay, so you get the equation for the force of the counterweight. So because the acceleration is 0, the force is the tension, the rope pulling it up, is the exact same as the weight pulling it down. And then for the block sitting at rest, the tension of the rope pulling it to the right is the exact same as the friction holding it to the left.
Yep.
And then so you set both of those equations as they're both equal to t, they equal each other.
And then you just simplify algebraically for the rest, and that's the answer for m.
Yep.
And then the next part is m is now heavy. It's heavier now, enough to make these blocks move. So it's asking what the acceleration is of these blocks.
The force of m moving is the same as the weight of it minus the tension pulling it back up. And then, so you solve for t. And then for the sliding blocks, you have the force of the blocks moving, and then you have the tension, which is again pulling it, pulling it that way, and then the friction, which is pulling it backwards. So you solve that one for t, and then you do the same thing as the other one, and set them both equal to each other. And then
the reason why these are together, that m1 and m2, is because they're a single unit, like they're stuck together. So these are moving as one single unit. And then kinetic friction is the only one considered because static friction is 0 when the blocks are already moving. So it's kinetic friction rather than static. And then that's your answer for acceleration. You just simplify algebraically. And now for part D. M is now heavy enough to move the blocks, but this time block 1 is slipping on block 2. So these are moving independently. So let's see here. Okay, yeah. So this the tension on what is this? For M2. Okay, yeah. So this is for this block. So for M2, the tension's pulling it this way, and it's kinetic friction's pulling it back, along with the there's two frictions pulling on this thing. It's the friction just from the one on the top, and then also the one combined both, because this one's resting on each other. And then you have to find the equation for m, which is basically just like F equals ma, but except F is just the weight of the thing going down and then the tension pulling back up. Let's see what else.
Well, and then you have to move algebraically, so you have to set both the equations to t, set them to each other, and then you can solve algebraically for this equation. So all the negative values are what are slowing everything down, and then the negative forces slow it down, the positive forces speed it up and it moves it, and then those are all divided by the mass because acceleration equals force over mass.
So that was for block 2. Block 1 is a lot easier to solve since it's just its own block. It's not resting on anything or whatever. So for that, the only like forces in play is just the friction pulling back on it, along with its own weight and stuff like that. There's no tension. Tension's only acting on M2. So even though it's moving backwards relative to M, it's moving forwards just for itself or whatever. I don't know.
Yep.
Yeah.
That's it.
I think that's about right. And then you simplify algebraically, you divide the m, and then you get that for the acceleration. Yeah.